Welcome to our webinar today on composites with Digimat. This is the first time that we've done a webinar with Digimat, and so our presenter, Gaurav Ghosh, has worked this all out from scratch. Well, there have been other Digimat webinars, but this is the first one on using Digimat for composites design for Formula SAE, Formula Student, and similar competitions. Gaurav is a senior technical specialist at Hexagon, where he helps solve real-world engineering problems using composite materials modeling and advanced simulation tools like Digimat. He earned his PhD from Vanderbilt University and has received several honors, including the 2025 SAMPE Young Professional Engineering Leadership Award. And I presented on composites last week in the webinar on finite element with Apex and Nastran. Gaurav helped me work out some of the scope for composites with that. And we've worked on coming up with some connections between our webinars. So if you haven't seen that one yet, you might want to go back and watch it. And I really look forward to seeing where Gaurav takes these ideas and what he has to share with us today about using composites to develop better formula cars, and using simulation to develop composites more economically and efficiently. All right, thanks, Gaurav. I'm really looking forward to the webinar.
Thanks, Alex, for the introduction. And with that, I will get started. So hello, everyone. Good morning or good afternoon, based on where you are located. In today's webinar, I'm going to talk about how to crack composite challenges in Formula SAE using Digimat, which is a Hexagon design and engineering software portfolio tool. And I think this webinar is well suited for this time because this week is actually National Composites Week. And we are really talking about how to tackle different challenges with composite modeling, despite of having so many benefits coming from composites. So let's get started with that. First of all, what are the pain points generally the student SAE teams are facing while it comes to composite modeling? The first one, obviously, is the accurate material information. Where do I get the fiber properties? Where do I get the resin properties? Where do I get the composite ply level properties? These are extremely important for reliable simulation or modeling, because composite material information is at the heart of everything. And if we don't get this information correctly, then everything else I do later down the road will be probably incorrect or not optimally designed. Then the second thing is layup optimization and coupon test. How do we decide which layup or stacking sequence would get me to the best possible or the optimized results? How do we decide on which coupon tests to run to test the performance of the material? And how do we decide that, okay, this is the material, this is the stacking sequence I want to go ahead for making my actual car part? Even though we have, let's say, some idea about the coupon test, it can be extremely difficult or painful to make those models like finite element models from scratch. So how do we do that efficiently? Then the third thing, the pain point is capturing the variability. How do we capture the variability that is inherent to this composite material production? Let's say when you do material testing, when you do the actual manufacturing, with all those processes, variability is inherently involved, and those variability can highly change the design decisions, like the peak strength that I'm getting or the stiffness. So how do we capture those variability effects through simulation? Then comes the study, the effect of defects, because defect, this effect of defects can have knockdown factors effects on your stiffness or strength prediction from a material point of view. These defects can be result of your manufacturing process, which is kind of honestly almost unavoidable. So how do we take into account those things and can still accurately predict how the composite is going to behave and how my final car part is going to behave? So all of those things we will discuss today. These are the common challenges and how we can solve them with like Digimat. So as I mentioned, like Digimat is the one-stop virtual solution for addressing all those challenges. There you can easily define like the test matrix, set up very efficiently and easily the workflow for the simulation and the design, then analyze and post-process the results, and probably like explore like advanced stuffs like variability, parametric sensitivity, all of those things. And this is very easy to do. We will show that today. With couple of clicks, you can get all the results that you need, which will reduce the need for like expensive and time consuming physical tests. Still, you can get like better decisions with like additional insights into it. And all of those things, most importantly, is both fast and accurate, which we all need. We don't want to go into very complicated like simulation things. And that's what we want to achieve with Digimat, where we can do all of these things with simple clicks. So the first problem, how do we get reliable fiber, resin, and pliable composite properties? So there are a couple of ways in Digimat where it can help you to get like the accurate properties. First of all, let's say if you have some lamina properties from like datasheet or database or test results. So datasheet values can come from the like material supplier. It can come from publicly available database, or if you have already performed some experimental tests, from there you can have those lamina properties. Now, if you have those lamina properties in Digimat, you can just input them here. What we are doing, we are inputting the tensile and compressive properties for transverse and longitudinal Young's modulus, the failure strengths, the shear strain, and like the shear strength, shear modulus, those properties, some basic matrix properties. If we have them, then we have a tool called like automatic reverse engineering, where you just click a button and that will give you a Digimat material card, like a digital twin of the actual material, where you can get constituent level behavior, the matrix properties and the fiber properties for this particular composite material that you tested for, or you get some data. Now, how do you do that? Let's play this video. So first of all, you just provide what is the material type. So let's say you are doing with a UD or unidirectional composite material. You just provide the name of the fiber, so carbon fiber, then like what is the matrix, the volume fraction, all those information initially to begin with. Then you go to material model, and here you just bring in the lamina level composite properties that you tested for or you got from some material supplier. So we will just input those things. So here, as I mentioned previously, you would input the longitudinal and transverse Young's modulus, the failure strengths, both for tension and compression. If you do not have a value for a particular like test, you have to like, you can provide the best guess value that you can get. Similarly, like you have to provide the values for like the shear experimental data, where you give the shear modulus and the failure strength properties, and some basic like matrix properties like density, Young's modulus, Poisson's ratio, all of those things you can get from like datasheet. And once you do that, here you see there is a button, calibrate material model. If you click on that button, Digimat will do automatic reverse engineering for you, and then you would be able to get the fiber and the matrix level properties, the constituent properties. So as I clicked on that, you see in matter of seconds or even less than that, you get like the matrix properties and the fiber properties of this composite material. And on the right hand side, you see like a stress strain curve for 0 degree, how the material will behave. And there you can change the loading to 90 degree, and in less than a second, you get what will be the stress strain response. So even without doing any further testing, you get all the behavior of this composite material that you want, and you can get it for shear as well. So once you do that, you can save and close. If you click on this button, this material card, the digital material card that you can use for your further simulation needs, will be saved on your local database. So there is no need of doing this process again ever. You have now the digital material card created, and you can play with this material card for further simulations that we will discuss in like a couple of minutes. So here you see this is the card we just created, and now this is ready to be used for further simulation needs. The second thing is, okay, you might not have like those experimental data or values from database or data sheet. What do you do then? So there is an option. We have a Digimat material database where you can just go and pick the data you need off the shelf from different material supplier. We have like data for continuous fiber from 6 different material suppliers for 27 different grades, and there are like already built in 128 Digimat cards, which are ready to be used for your simulation need, as I am showing here. So even if you do not have any experimental data, any information about the material, but you still want to get one material card for your use, or like multiple material card that you want to use and pick and choose, you can directly do that without doing any physical testing ever. And these are all reliable, calibrated data for you. So how to do that? So first of all, on the left, you see like you can pick filters. I'm picking filters for continuous fiber UD and continuous fiber woven, let's say. Then you can also pick filter for like what is the filler material. You want carbon fiber, glass fiber, or any other particular thing. In the matrix, what will be the resin that you want? What will be the part performance? What will be the process simulation that you are interested in? What is the model behavior? Elastic, plastic, whatever, thermal dependency. What is the temperature condition for which you want to get this data? What is the moisture condition for which you want to get this data? So you can do all this filtering to make your search much more easier and focused. And once you do that, then if I go to table view, here you see you get all the names of the data supplier, the trade name, matrix, filler, the fiber volume content, then what is the matrix model, whether elastic or thermoelastic, whether it's for structural performance or some other thing, then what is the unit, the temperature, the relative humidity. So all of those things are sorted, and based on your need, you can pick and like just use the material card as it is. Then you can plot the stress strain curve as well, where readily you will get some idea about how the stress strain curve looks like, what is the like peak strength, what is the failure strain, all those information. You can also click on this button, and then it will show you even like the fiber and matrix level information for all of those grades easily. You don't have to go anywhere else. Here I'm showing like you can like do the filtering for a particular, like let's say carbon fiber, and now everything you see here is for carbon fiber. So it's really easy to use, couple of clicks, and you get all the information about a material that you need. But by doing this way, you can like eliminate the need of doing like extensive physical testing by yourself. Then the third thing is, okay, let's say I got the fiber and the matrix properties from some material supplier or somebody, but I don't know, like if I mix like 30% of that fiber with the resin, what will be my composite response? What if I mix like 50% volume fraction of fiber with the resin? what will be my composite properties. Let's say I want to change the layups from a single layer analysis. I want to do a multi-layer analysis. In the multi-layer analysis, I want to change the stacking sequences. What will be my composite level response? So without having a reliable simulation tool, what you need to do, you have to do like all those expensive experimental testing for each one of those cases. And that is kind of like honestly not possible all the time. So that's why we have a tool in Digimat where you can virtually predict the composite level response. Once you have some fiber and matrix information, you can go and just change those properties, all these parameters, and it will give you all the composite level response virtually. So how to do that? So let's say we started with a material card from our database. Now we open the material card. Here we see it is showing the carbon fiber like properties. We can change those properties if we want. We can change the model, the elasticity symmetry. Similarly, we can do it for the resin, the epoxy system, and see what will be the response. Then here we have an option to change the volume fraction of the fiber. So let's say we started with like 55% of the volume fraction first, and then like we started with a single ply. So within a couple of seconds, you will get what will be the stress strain response for this particular material. We can also get the engineering constants like the Young's modulus in like transverse, longitudinal, all those directions for this particular material. Now, let's say we want to change the volume fraction to 30% and want to see how that will affect the composite level performance. Without doing any physical testing, in seconds, we will get the stress strain response. So you see, as expected, we changed the fiber volume fraction, we decreased it, and as a result, we get a weaker stress strain response. Here you get all those engineering constants for three directions like Young's modulus, the Poisson's ratio, the shear modulus, the density. You can directly take these values and you can go to a FEA tool like Nastran, Mark, or like Abacus, whatever you use there, and put these values for your part level analysis. You can similarly do like here, let's say now instead of having a single ply, I want to have like multiple ply with a stacking sequence of let's say like 0, 45, 90, something like that, and like with a pattern. So we can just add like multiple layups. Just copying those things. Now created like a multi-layer analysis. And here we get the stress strain response for this particular case. So you see, like with some clicks, without doing any physical testing, anything like without doing any complicated like analysis, we can very easily in seconds can get the composite level response. Now, with that, we are settled on how to get accurate material information. Now, how to decide on the best possible stacking sequence and the coupon test. I was just selecting like random like layups, but how do we decide that, okay, this is the stacking sequence I want to go ahead. This is the coupon test that I want to perform. So for that, in Digimat, we have like a pre-created database where you can just pick and choose again, like whatever layups you want to have, like quasi-ISO, shear example, just UD, and you can choose like multiple layups at once and do like parametric sensitivity study in Digimat. You don't have to like create a FEA model by yourself for these stacking sequences. Now, let's say you want to do some custom layup that are not available in the database. There you go. You can create your custom new layup where you can just provide the stacking formula, or you can just provide those things like, let's say it doesn't follow any formula you just have some like random layups that you want to try. Yes, you are of course free to do that. You can just put those like numbers here and like let's say apply symmetry, create from stacking formula, whatever you want to do, and your new layup would be ready to use. So how to do that? So first of all, like let's say I'm selecting something from the pre-existing database. I want to try like 3 different things. So now I'm creating my layup, like the custom layup that I want to do. I'm creating from stacking formula once I give the stacking formula, and then I want to apply symmetry. Now this is ready in a minute. Once I do that, then here, like as you see, I am trying and testing like 3 different stacking sequence at once. Now, if I want to save this stacking sequence on my database so that the next time I use this software, I don't have to like create again this particular stacking sequence, you can just save it in the database, in your Digimat database, and it will be ready to use for the next time. For the coupon test, there are like tests defined by the industry standards. There is a long list of tests already available in the Digimat database. What do I mean by that? Here I am showing some like examples like unnotched, field hole, like 4-point bending, open hole test, V-notched, 3-point bending. There are multiple tests. For them, we already have FEA models built in. So you don't have to choose, and you just don't have to like prepare that FEA model from scratch. You don't have to like create anything fancy. You just go there and pick and choose the pre-built, pre-existing material, the FEA models, which are built according to like ASTM standards. Now, you might want to try and test for like custom configuration, like different dimensions. You can easily do that. You can just have to like give those numbers, and Digimat will create the FEA model for you. You don't have to build it from your CAD. You don't need any CAD, nothing. How to do that? Let's play this video. So here, for example, you see like these are like all the different tests that are available in the database. Let's say I'm doing for unnotched tension. You can change the unit system to whatever you want. And then these dimensions are according to ASTM D3039. You can choose your custom dimensions and change those things if you want. I'm just showing like I'm changing the dimensions and making something else. You can do the same for the others as well, and you can have like multiple tests selected at once. And then again, run the parametric sensitivity study like very accurately in a fast manner, which is almost impossible if you have to do everything from scratch. Even if you are doing like with standard FEA softwares, there you need like CAD models for all of those things to be built in, and then meshing and doing all those things. But Digimat is taking care of you here with some simple clicks. Now, the next thing is like how to capture the variability, because this variability is expected during production, like coming from like several sources, and it is extremely important to capture those things for reliable and accurate predictions. So first of all, like in Digimat, when we do the variability analysis, it is based on the US military handbook. We want to compute the allowables based on the variability, which is expected during manufacturing. It is unavoidable. In Digimat, we do variability in 3 stages. The first is at like the materials level, where let's say my fiber and matrix properties would have some variability. So we call it like constituent level variability, how to capture them. Then comes like the process variability. From your manufacturing process, there would be some variability, how to capture them. Then the third comes like the post-process level variability. What do we mean by that? So first, the constituent variability, which is taken care by the batch, where on the right, you see like if you have variability in any one of these like material parameters, you want to capture them. you just do that. So Young's modulus, the strength parameters for matrix and fiber both, you can do that. Then comes at the panel, which is at the process level. If your fiber volume fraction or like ply misalignment, all of those things you want to capture some variability or standard deviation, you can do that. Then comes the specimen level while doing the testing, so post processing kind of, where you can have like coupon misaligned. If you want to capture that variability for your like the prediction, you want to take into account all of those variability in these three level, and it will help you to get accurate allowables. How to do that? Let's see. First, you have to select the material, the layup, the test coupons, and the environmental conditions. So all of those things are already available in Digimat database. And then next comes the variability definition. The standard workflow takes like no variability, but we want to go with like some military handbook like variability that we want to do. Here, you just have to provide how many number of batches, how many number of panels, and how many number of specimens you want to play with. That will define your total number of configurations for doing this variability study. You can change those numbers if you want. You click on this, you go to that Digimat material model that you created, and here you just have to define those individual variability for those three levels, like the batch level, the process level, and the coupon level, like the test levels. So you can give whatever number you want. This number can come from your experience or from material supplier. You can do like parametric sensitivity as well on those variability values. Once you generate those jobs, here you can see like the variability post processing. It will give you a probability distribution of all those values. What is the nominal value? What is the standard deviation? What is the coefficient of variation? What is the number of draws? All those information for different choices that you made. So once you have that, you are ready to run like those 18 jobs in this case. So basically, Digimat will run 18 FEA simulations, and at the end of the day, you will get like 18 different load deflection curves, let's say, or like stress strain curves. That will tell you like what is your mean prediction, what is your like standard deviation, all those information. Now, the final thing is like how to study the effect of defects, because this is important. As a result of defects, you will have knockdown factors that will reduce your coupon strength, and we want to accurately capture that. So how to do that? First of all, like we want to understand from where these defects can come. In Digimat, you can have defects coming from like 4 different sources. One can be like waviness. So that can be a result of like poor layup, resin flow during cure. There can be initial delamination, which can be caused by like defective bonding during cure. There can be porosity, which can be result of like incomplete resin infiltration, improper cure cycle. Now, porosity can be both intraply or interply. For the intraply, this is the porosity in the ply itself. Interply is the porosity between the plies and at the interfaces of the plies. And there can be like automated fiber placement gaps. So toe misplacement, these gaps can be a result of the automatic fiber placement manufacturing method. So all of those things are pretty common to happen during manufacturing. And on the right hand side, you see a stress strain curve. So the blue curve shows the pristine configuration if you didn't apply any knockdown factor on the strength, and the green curve shows knockdown factor applied due to the result of these like defects. And you can see like if you do not use an appropriate knockdown factor, you will significantly overpredict the strength and stiffness of the coupon, which is not accurate. So it is extremely important to take care of this. Here is an example how to define like, let's say, porosity. So on the left, you see you can define porosity as a global level for the intraply, where let's say I'm doing a porosity fraction of like 0.06, so 3% porosity. But that will be applied or distributed over the entire coupon. And on the right hand side, I'm doing it at a local level. So on this yellow box, only here of this location of the coupon will have this particular porosity. You can define like multiple porosities in your coupon as well. Then comes like waviness. Another example I'm showing here, you can define like multiple different types of waviness, like of the plies that it can have. So it can be like uniform, there can be like hump, indentation, embedded, or you can have your custom geometry, how the like the fibers would move like out of plane on those places. So you can again like select the region where you want to have. You can define its amplitude. It's like the maximum amplitude, amplitude type, all those information, and based on that, it will have some defects inside it. Now on the right hand side, I'm showing like you can do also sensitivity study on the defects, because if you just consider that, okay, this is an unique defect type in my coupon, and I want to have a knockdown factor predicted for this particular defect type, that is probably like not very representative of what is going on in reality. Ideally, you should do a sensitivity study, because different coupons will have different types of like these defects. So the wavelength can vary, the maximum amplitude can vary, your position can vary a little bit. So you want to do a probabilistic distribution and then run a sensitivity analysis. So in Digimat, on the right hand side, you can see with some like numbers and some clicks, you can easily perform all this sensitivity study for the defects and can go close to the reality. How to do this defect study? Let's see. So again, like the basic steps are like you have to define the material, you have to define the layup, you have to define the test, you have to define the environmental conditions, and you can choose like all of them from the database, or you can select as per your requirement. You can just define those things. You just do like defect study. And here, if we click on the defects, I just have to go and define, let's say I'm doing for waviness. I can change the position, I can change the wavelength, I can change the orientation, the amplitude type, the maximum amplitude, where in my coupon the maximum amplitude happens, all those information I can change. And I can define like multiple defects, because in reality, that can also happen. So once you have that, then Digimat will create the FEA coupons for you with these defects in it, and Digimat will run the FEA simulation. And at the end of the run, you will get to see all the results, and you will get to see like the pristine stress strain curve versus the stress strain curve with defects in it, because there will be some knockdown factor applied to it. Now we come to the fun part where, like, let's say, yes, we defined all of those things. How to analyze the virtual strength and the stiffness of the composite coupons. So basically analyze and post-process. Here, like you see a sample like screenshot where you can do the plots for all plies or all the plies like separately, like ply 1, ply 2, ply 3, or at the interfaces, wherever you want. And this shows like what are the like the output variables that you can see. That can be stress, that can be strain, that can be damage. And on the right hand side, like you see with time how the stress strain curve evolved. You can track that with this little like ball or the point. So it will move as you drag this slide bar. It will just show you where at the stress strain curve you are at, and also the contour plot here would change. So you can do that. You can generate like automatic report. You can create like animation. You can take screenshots, whatever for your like let's say final report or final presentations. So it's really easy to use. You just have to click on a couple of places, and it will create all the results for you, the reports for you that are ready to use. So now with that, this is a short video showing like the complete workflow that I just mentioned, like different aspects of it. So let's just play it. So again, like first, we want to define the test matrix. On the top, you see the test matrix definition involves like this materials, layup, test, and environment information. I covered all of those things already. The next thing is the variability definition. Depending on your use case, you can define the variability. This also I explained. So here it is showing to that, like, okay, it will define the variabilities, like I mentioned, for the constituent level, the process level, and the test level. Then you just generate those FE analysis. It will create all the jobs required. It will show you like for the 3 levels of variability that you just defined, how they look like, the probability distribution, the standard deviation, the coefficient of variation, all of those information. And then you can just submit the job. You can submit it on your local computer. You can submit it on cluster, wherever you want. It's really easy to do all of those things. You can do it from one interface. Here you see the histogram and the distribution functions for like strength and stiffness. You see like A basis, B basis value. So basically A basis means like 99% of your samples should cross this value with 95% confidence. So this is more stringent criteria. You should usually use this A basis value for design of your critical component where you want to make sure they will not fail. The B basis value is a little bit less stringent, where it says like 90%, at least 90% of your samples should cross this value with 95% confidence. So you can use that value for like some members in your design, or like some parts of your design where they are not that critical. There can be like, if these members fail, there would be ways to redistribute the load path. Here again, like if you go, you can play with all these displacement variables, the stress variables, whatever you want to see for all different plies, all plies at once. So this is really handy. Like it is showing, it's really nice. And you can then generate your report. This report will have all the information about your test matrix definition, the variability that you defined, and then how the allowables look like, then the results from your like global and local post processing. So this gives you like overview of the entire thing that I just discussed in brief, and you can really see these are like very easy to follow. With some simple easy clicks you can achieve this, but at the end of the day it will give you deeper insight into what is going on in your design. Now with that, let's say we have arrived at a point where we have idea about the material, we have idea about the layup, we have idea about the variability, the effect of defects, all those things. And now I am ready to apply this material and the stacking sequence on a real car part, the bigger car part, how to do or how to predict the structural performance of that real formula car part made of composite. So Digimat has a streamlined workflow for that. You need a FEA model that can come from like MSc Nastran, that can come from like MSc Mark, that can come from like Abacus, ANSYS, LS-DYNA, whatever you use, or like any other FEA solver. You have the material card already built in Digimat. You just created that, or you can get any of the material card that I showed previously from our database. Those are already pre-built. You just combine them in Digimat and then run the finite element simulation from the Digimat interface itself. You don't have to go anywhere else. Just simple clicks. I will just show that. Once you have the results, you can post-process it in like post-processors like Patran or like Mark Mentat, or in like Abacus or any other like post-processor where you can open those results files and see like composite level stress, composite level like strains, or like ply level stress, ply level strains, everything, like whatever you expect from like a finite element analysis as output. You can see the damage, the failure, how like the load displacement curves looks like, all of those things. So the first thing that you do in Digimat is you bring in the finite element model. You can see the details of the finite element model. Once you bring in that, then you can define the manufacturing process as for like continuous fiber reinforcement process, because this you are doing for UD, so CFRP process, and the type of reinforcement is unidirectional reinforcement that you are using, or UVEN, whatever you are using. Then you like add the Digimat material card. You can use it from Digimat MX, that is our material database, which I showed previously. From there, you can just go and pick and choose like off the shelf, or you can choose it from file. So that can be like you calibrated it like the automatic reverse engineering that I just showed. Like if you have the test data from there, you want to build one material card, you can do that. If you have your fiber or matrix level properties from there, you can build that. I showed that as well. You can play with all of those parameters. So whatever you want, you just have to bring in that material card, select the units. You can see its stress strain response again here and all the properties. Now you're done, actually. You just have to submit now the job. Once I run the jobs, once it gets completed, you can go to the post processor. I am using Nastran and Patran for the run and the post processing. There, let's say I want to plot like composite stress, like the ply level stresses at the end for a particular ply. I just select which layer I want to do that, and you can see the results. I can do it for like whatever ply, whatever output variable I want to do. So the key takeaways of what I just showed, this entire thing, it like, again, if I want to highlight, it solves the major challenges in composite modeling for the Formula SAE teams. You can get accurate material information for the fiber, for the matrix, and for the ply level, either from experimental data. You do automatic reverse engineering, calibrate your own digital material card. You can pick and choose from our off-the-shelf like material suppliers from our database. So all of those information are readily available for any users of Digimat. That is an extensive database, all calibrated. You don't have to do anything else. Or you can create your own material card starting from fiber and resin level properties. You can play with the stacking sequence and all of those things, volume fractions, and you can create your own custom material from virtual testing. Then you can capture the variability in all of those process parameters, your material parameters, your test level variability. You can also study the effect of defects for different types of like manufacturing defects that can happen, waviness, porosity, delamination, AFP gaps, and get the knockdown factor, which will affect significantly your stiffness and strength predictions. So all of those things will reduce your expensive physical test. It will save you both time and money, which is, I think, like crucial for like student teams going into these competitions. And then it gives you a streamlined, easy workflow to follow for formula card part performance prediction. So Digimat can be your one-stop virtual solution where you can do all of those things, solve your major challenges that you see in the way of getting you guys to the winning position for this competition. With that, I just want to like show like a live demo one more time to highlight what I just discussed for the entire thing. So first of all, you have to go and create a material card. Okay, so you can do that. Like you define your name and the fiber name, the matrix name, the nominal volume fraction, the cured ply thickness, something like that. And then you can pick and choose like from the database. if you already have calibrated that material. If you do not have that already available, what you can do, you can go here, go to database, and let's say I want to create a new one. I'll just write that name, whatever it is, creating one. Then I go to material models, and here for the experimental data, I will have to fill in all those information. These are already pre-filled, but in your case, like if you want to do it from scratch, you have to fill in these ply level properties. Once you do that, you give some basic like matrix and fiber properties. I just click on calibrate material card. If I do that calibrate material card, the Digimat material model will be created for me. The matrix level and the fiber level properties are automatically reverse engineered, and you get that from the composite properties. Here I can see, like, let's say for 0 degree, the strength is 2500. I can just click for 90 degree and see what is the strength. I can do for shear. Once I'm happy with all of this information, I can just save and close. If I do that, this material will be saved on my database. So that's how I choose this material. Then I go to the layup definition. I can pick from database, or I can create my new layup, whatever I want. So let's say I want to do something. So I can do that. I can select whatever material, like the layups I want. Then I can do for test as well. Let's say I want to do for like in plane shear, like V notch, and then just select. So I'll get another like test in there, just deleting it. And then like I can do for environment as well. So there are some predefined environment like cold temperature, the room temperature, the elevated temperature. I can define my new environment as well. Let's say you want to test your coupon or the part at a very specific condition that you can do here. Then you can go to the variability study. Here, you can define the number of batches, the number of panels, and the number of specimens that you want to have. Once you have that, it shows you the number of tests to be run. And here, if I go there in the Digimat material, I have to define the variabilities for the constituent level, the process level, and the testing level. And I can define for as much like number of parameters I want. So once you do that, you are ready to run the simulation. Here you can have a quick look on the variability post-processing for the different variables for which we define the variability, the standard deviation, the nominal value, the sample mean, all those things. And then we click on generate jobs. Here I already did that because it will take some time to run the finite element simulations, like a couple of minutes. Once we have the jobs run, we can click on this and it will give you those A basis and the B basis values for strength. If you have like for stiffness, it will also show you that the standard deviation, the mean, what are the thing. You can also show like the raw test results for different tests, as you can expect. Like you see here the variability in our test results. Because we defined all of those things, then we can do like local post-processing. Now we click on that. Here you see like for all the different tests that I run, I can see the results. And then I can go for each ply level separately or all the plies at once. And also I can do for displacement, for the normal stress, the reaction force, and what are the components that I want to see. Also, I can like drag this thing. And here you see the contour also change, and you see at what location at your stress strain response you are in. Now, the final thing, I can go to report and just click on generate report. It will generate a nice Word document with all of those sections, like the data, the test matrix, the Digimat model, the laminate theory estimate, the FEA settings that you use to do these finite element simulations, and then finally like allowables and the user created plots that you just did. Now, once we have all of these things, we are happy with the calibration, our stacking sequence, and all of those things. We can just take those material, then we go to Digimat MS in Digimat, and there I can just bring in this new material card. Let's say we want to do with this. Select the unit system that you have. In this particular case, I have like a honeycomb sandwich panel, like a aluminum honeycomb, and with this red thing defining the composite material. So I can just see that selected component if we want to do. So it can be handy if you have really complex part. You can just pick to see that particular part where you want to apply the composite material in your viewport. Select like CFRP process, unidirectional reinforcement. Then I add Digimat material, click on file and select the material card that I created already. Once we have that, we define the manufacturing data, and there's nothing to be defined. This stacking sequence will take care of it. And then just click on this play button. Once I confirm and submit the job will start to run. And once the job gets completed, I can open this on a post processor like Patron, for example, and there I can see all the results that I want to see. So composite level ply stress, for example, I want to see like composite level ply strain. So similarly, I can do it for whatever I want to do. Another thing I wanted to highlight, so in Digimat MF that I was mentioning, in Digimat, let's say I have those epoxy and carbon level properties, the carbon fiber properties. I want to change like volume fraction. I want to change the stacking sequence and see its responses. And I can do that easily. Here, let's say for the settings that I had, this is the stress strain response I get. These are the engineering constants I got. So let's say for E11, we just highlighted that 131,000 MPa, maybe the E11 is. So now I'm changing this volume fraction to 0.3. So basically I'm making the composite weaker. And also let's go back here. We are seeing like the failure occurs around like 0.015 strain. If I'm making it weaker, like changing the fiber volume fraction, our guess would be the material would get more ductile because matrix or the resins are more ductile. So we'll go towards that. And also our E11 value should decrease from 131,000. So let's see what we get. And we're doing it all virtually, no testing, nothing. You see, now this green curve is a new curve that we get. It got more ductile as we expected. So basically failure strain increases. But if we go to the engineering constant, this value, the E11 has significantly decreased as we have expected. So we can play with all of those things. We can go to RVE and create a multi-layer analysis if we want to do that. So basically we can create our own stacking sequences like 0, 45, 90, all of those things, what will be the thickness, and play with all those information. Similarly, like if we don't want to do any of these things for material definition, we can just go to our Digimat database for the material and select for the continuous fiber, the filler, the temperature, the moisture content, and I will already get the readily available data. All of those information are already available there. You just have to pick and choose. I already showed a demo of all of those things through my videos, like pre-recorded videos, but I just wanted to highlight all of those different components one more time to just like provide more value and like just reinforce that learning. With that, I want to end my presentation. Thank you. And you are welcome to visit our Hexagon website, our Hexagon Digital Materials website, and contact us to get more information. We'd be happy to answer all of the questions you might have and help you win the SAE competition. Best of luck with that. And I'll leave the floor to Alex. He would make some like announcements here. So Alex, floor is yours.
All right, thanks, Gaurav. That was a really interesting webinar, and I hope that the people who attended find it helpful. And so I want to tell you about how you can follow up and how you can try out these Digimat skills yourself. if you're on a Formula team or really any student competition team, if you are part of a group of students at your college or university and you're doing an organized activity together, you can apply for a student competition bundle at the link that you see on the screen. And I'm about to share some links in the chat in the next couple of minutes. With that, you get full commercial releases of our software for all of the many products that we have listed here. For the student editions, those are a little bit easier to apply for, and those are available for any student or professor. Now with those, the model size is limited. So, you can only deal with models that go up to a certain size. We have one webinar coming up, only one webinar remaining in this series. Next week, it's going to be on generative design and topology optimization with MSc Nastran Sol 200 Neo. You can follow along with the webinar series at the link that you see on the screen, which again is going to be in the chat or on YouTube in the description. We are posting these webinars on YouTube, and you can follow us on LinkedIn for updates. Gaurav, I think that we are ready for questions. I see one listed here. What test was done for deriving these properties?
For deriving the ply level properties, we followed like ASTM standards, like simple tension test or shear test. So really depends on what you are trying to model. So for example, here we want to have the ply properties like the Young's modulus, the failure strengths. Those things you can get easily from like ASTM standard tension tests. And then we need like shear tests to get those shear properties. So these are the like basic tests. We have an extensive like document, Digimat user manual, which lists all this information. If you want to dive deeper or like just contact us, we can discuss more. Depending on your needs, we can suggest which way you should go.
I had seen something about the properties having to do with NIAR's NCAMP.
Yes, yep.
Okay.
NIAR has a like good recommendation that we also follow. Yes, like
okay.
AGAT, AGATE, in like NIAR database. Yep.
Okay, great.
Yeah. Many of the data sources from the MX database were NCAMP sourced. So you can see columns there, and here on screen, there's a source column as well.
Yeah. There is like other columns on the right hand side that is not visible from the screenshot, but yes, you can see all those information.
Awesome, great. Do you have suggestions on where people should go to start learning Digimat? Like, where would they go to look for basic tutorials to get started?
So one awesome place would be just to get like quickly started with Digimat is if you install Digimat. With that, in the examples manual, we have real short videos that you can just watch on the YouTube channel. I guess like there are a couple of videos, and also you can go to our Hexagon website, the Nexus Documentation Center. There you get like more information about like how things work with Digimat. So I believe like there is also like the Nexus Training Academy. There one can go and look for like different pre-existing like tutorial videos or like materials on this aspect. My suggestions would be to go to those places and probably just rewatch this webinar on YouTube, the recording of this.
Sure.
It shows like quick demos. Once you have the Digimat software, you can just try to follow along those steps.
Yeah, and it really seems like you can pick up value from Digimat incrementally, right? That even if you're just pulling material properties, that's a useful thing.
Correct. Yes.
And so you can make more and more use of it gradually. You don't need to know it all at once to do anything.
Absolutely. Yes. You can choose a material, you can choose a layup, you can choose a test specimen from the database to just start with. And once you get a good hold of that, then you can play, like start playing with your own values or like bringing in your own test data and doing some more advanced things.
Do you have any suggestions on troubleshooting skills, or are there any errors that Digimat users who are new to Digimat seem to make frequently?
On the material aspect, I can think of like if you give like non-physical data, for example, that can be a challenge for like creating the constitutive material. But Digimat really gives you very helpful error messages when it comes to these material properties. So really, you just need to understand English. If you can do that, you will be able to see like, okay, where it is pointing out. It will tell you that, okay, it is not it is actually like violating some of the physical like equations that it needs to follow. So that can be one thing that one needs to be aware of. There can be errors with like unit systems that are like a very common thing. You have to be consistent about the choice of your unit system. So everything should be in SI unit, or everything should be in like FPS unit. Whatever you pick, just stick with that. That will be my suggestion. And then the third can be like when you run like a finite element simulation on your composite part, there can be like convergence issues that are like always inherently possible, but and existing. But Digimat again like will give you helpful error messages on why this is happening. This might be due to like the material properties that you chose was not good for convergence. So just try to adjust them. Or it might be due to your stacking sequence that was probably like too soft, or like not like very good about like capturing the or like carrying the load that you wanted to do. But really, I would say it's extremely straightforward compared to many other FES softwares that I have used. And this is really easy to understand and troubleshoot the error messages that you get. And also, if you go to our documentation, again, I will just point out there, there we have already like written many of these like the tips or like the troubleshooting advices or the error messages that you might get. You can just go in there.
Great, thanks for all of that. Gaurav, did you have any further thoughts to share?
I would say just I encourage the students and this Formula SAE team competition guys just to go explore Digimat, just rewatch this video. I hope this would be helpful in addressing all the composite challenges you might have, and you can have a pretty accurate, efficient workflow for modeling composite and getting a very robust design for your part. And always you can count on us. You can come to us if you have any question while using Digimat. This is the industry standard for composite material modeling. And I think like this will be an extremely useful tool on your hand.
Great, thanks, Gaurav. I really enjoyed learning more about composites with you, and I look forward to seeing what great things students are going to be able to do with Digimat in Formula SAE and other competitions that are similar. All right, thanks everyone. Have a great day. Bye.
Thank you.